All right, to continue section 4.3, curve sketching, I'd like to use a little bit more difficult problem. Okay, this is a quotient here, it's not just a polynomial. And so when we deal with quotients, you will be asked for domain, vertical asymptotes, horizontal asymptotes, and then finally the first derivative test, second derivative test. So the first thing we're going to do is we're going to find the domain. So the domain here, we can't divide by 0, so x can't be positive or negative 3, so I'm just going to say x can't equal plus or minus 3, right? The second thing we're going to do is we're going to find the vertical asymptotes. So if you remember, a vertical asymptote occurs when we divide by 0, which is occurring here at positive and negative 3, right? So I'm going to use the calculus method to determine the behavior near these asymptotes, right? So I know there's an asymptote at positive 3, and I know there's an asymptote at negative 3, because that's what makes the denominator 0, and there's no way to get rid of those points. So I'm going to evaluate the limit as x approaches 3 from the negative side, and the limit as x approaches 3 from the positive side, as well as the limit as x approaches negative 3 on the negative side, and the limit as x approaches negative 3 on the positive side. Now the way we evaluate each one of these limits is we pick a test point, okay, because there is no way we can cancel this or factor and reduce it, and we know it's an asymptote, so I just want to know whether it's going to positive or negative infinity. So a test point here on the negative side of 3 would be 2.9. So 2.9 is less than 3, so when I square it, it's 8 point something. Okay, and so we're going to get something less than 9 minus 9, so this is going to be negative infinity. Okay, if I pick a test point greater than 3, like 3.1, okay, when I square 3.1, it's going to be more than 9, so a bigger number minus 9, this is going to be positive infinity. Right, a test point on the negative side of negative 3 would be negative 3.1. And so again, when I square this, it's going to be bigger than 9. So the answer is positive infinity. And then if I pick up a number on the positive side of negative 3, we're looking at negative 2.9. So when I square this, it's going to be less than 9. So the answer is going to be negative infinity. So I know what the behavior is doing near the asymptotes. So what about the horizontal asymptotes? The rule is, right, if the degree of the top is less than the degree of the bottom, the asymptote is at 0, right? So this one is going to have a horizontal asymptote at 0, if you will. So then finally, let's go ahead and do find where f is increasing and decreasing, as well as find where it has maxes and mins. Right, so in order to do that, we need to take the derivative. Now I'm going to spare you taking the derivative here. I'm just going to go ahead and give you the answer. You might want to make sure that you can get the right derivative. Go ahead and do the quotient rule on this and make sure you can get the right answer. But for now, I'm just going to give it to you. So the derivative is negative 2x over x squared minus 9 squared. So I want to find the critical numbers here. So the critical numbers are where the derivative equals 0 and where the derivative does not exist. So the quickest way when you have a fraction here is you set the numerator equal to 0 to find where the derivative equals 0, and you set the denominator equal to 0 to find where the derivative doesn't exist. So I'm just going to take the numerator, set it equal to 0 to find those critical numbers. And then I'm also going to take the denominator and set it equal to 0 to find the critical numbers where it doesn't exist. So I'm going to get a critical number at 0 here by dividing both sides by -2. And then here, we'll square root it. Move the 9 over. And I'm getting critical numbers at plus and minus 3. So I have 3 critical numbers. One where the derivative equals 0, hence where the numerator equals 0. And 2 where the derivative does not exist. So I'm going to go ahead and do a number line analysis now. Put 0, -3, and 3 on there. So since I have 3 critical numbers, I'm going to have 4 intervals that I need to test. Right, so I'm going to pick 4 different test points. So a test point between -infinity and -3, I'm going to pick -4. A test point between -3 and 0, I'm going to pick -1. Between 0 and 3, I'm going to pick 1. And 3 to infinity, I'm going to pick 4. Right? So we want to plug those test points into our derivative. So our derivative is a -2x on top and x squared minus 9 squared on the bottom. Right? So anything we plug in here, we're going to square it, and it's going to become positive because, you know, negative squared is positive. So that's actually not going to change the sign. So the only factor that really matters is the -2x. So what happens if I plug -4 into -2x, right? Or each one of these test points into -2x. If I plug a -4 in there, it's going to make it positive. So this is positive here. If I plug a -1 into this factor, I'm going to get a positive. If I plug 1 into here, I'm going to get a negative. And if I plug 4 into here, I'm going to get a negative. Right? So really, it was only the numerator that mattered because the denominator was always going to be positive. So I know the derivative is positive on the first 2 intervals and negative on the second 2 intervals. So the first derivative test, or the increasing-decreasing test, says if the derivative is positive, then the function is increasing. So we're increasing on these 2 intervals, and we're decreasing on these 2 intervals. So I'm going to go ahead and go up here and write those down. So we're increasing from -infinity to -3 union -3 to infinity. And even though these intervals are side by side, you don't want to include -3 because remember -3 happens to be an asymptote, right? So there is going to be a break in the graph. So we want to make sure we're showing that in our increasing-decreasing intervals. All right, so it's decreasing on the other 2, 0 to 3, and 3 to infinity. Okay. Now, the first derivative test is looking for maxes and mins. It's looking for a change from positive to negative, or negative to positive. And we have only one change that occurs here at 0. So is 0 a max or is it a min? Well, it's increasing on the left and it's decreasing on the right. So it looks like 0 is going to be a local max. So we have a local max at x equals 0. And we have no local min because it's never changing from negative to positive. So there's our first derivative test. So then we want to do our second derivative test, our concavity test. And in order to do that, we want the second derivative. Okay, so the second derivative, even worse than the first, right? Because we need to take the derivative of this. So I'm going to go ahead and give you the derivative. I challenge you to see if you can get the right answer. But for now, I'm just going to tell you what the second derivative is. So the second derivative of this function is going to simplify to 6x to the 4th minus 36x squared minus 162 all over x squared minus 9 squared. Right? And I got that using the quotient rule. And so in order to do the second derivative test or the concavity test, we need to find the critical numbers yet again. All right. So I am going to set the numerator equal to 0 and the denominator equal to 0. So if I do 6x to the 4th minus 36x squared minus 162, you might be thinking, how in the world are we going to solve that? I want to know if 162 is divisible by 6. Yay, it is. Okay, so first thing, we could take a 6 out. But this is setting this equal to 0. Let's go ahead and take the 6 out. So I'm going to get x to the 4th minus 6x squared minus 27. Okay. So can we factor this? Do we know two factors that multiply to negative 27 and add to negative 6? 9 and 3, negative 9, positive 3. I do think that'll work. Okay, so I am going to factor this. X squared and x squared, negative 9 and positive 6 here. All right. Nope, not positive 6. How about positive 3? Now that works out. Okay, I was boiling and I was like, this is not the right answer. So negative 9x squared plus 3x squared, and then the minus 27. So in order to solve this, I'm just going to set each factor equal to 0, including the 6. All right, and then I'm going to get x squared minus 9 equals 0, and then I'm going to get x squared plus 3 equals 0. So this one has no solution. If I add 9, take the square root, I'm going to get plus or minus 3. And then here, if I subtract 3, I get x squared equals negative 3. This has no real solution. It's imaginary, right? So I get two critical numbers. Now it's just setting the numerator equal to 0. If I set the denominator equal to 0, again, I think we're going to just get plus or minus 3. So the critical numbers for where the derivative equals 0 and where it doesn't exist are the same. So I'm going to go ahead and do a number line analysis with the second derivative. Okay, so I have two critical numbers. So I'm going to have 3 intervals. So I'm going to pick a test point in each interval. So negative 4, 0, and 4. And then I want to plug these values into the second derivative here. So I think I'm going to opt to use my calculator here. So I'm going to put this into my y equals 6x to the 4th minus 36x squared minus 162 divided by x squared minus 9 squared. Okay. And then I'm going to use my table to evaluate these at my test points. All right, so at negative 4, I get the second derivative is positive 16. At 0, the second derivative is negative 2. And at 4, it's a positive 16 again. So we have positive, negative, positive. Now this is the second derivative, SIGNs. And so if the second derivative is positive, then we know the function is concave up. And if the second derivative is negative, then we know the function is concave down. So I know that this function is concave up from negative infinity to negative 3 and 3 to infinity. And I know it's concave down from negative 3 to 3. Okay. Then we want to talk about the inflection points here. So inflection points occur when it changes concavity, right? So it is changing concavity at both negative 3 and 3. So I'm going to do negative 3, f of negative 3, and 3 comma f of 3. But if you remember, 3 and negative 3 were the asymptotes of this function. So since this does not exist, and this function value does not exist because it's an asymptote, there are actually no inflection points here, okay? Because the concavity is changing where the asymptotes exist.